Hello, everyone, and welcome to this episode of our brand new Inspiring Science Education Hangout series. My name is Dr. Pamela Gay, and I'm going to be your host for hopefully the next couple of years as month after month we bring you new opportunities to learn how to get science better into your classroom and your outreach activities. In this series of live events and training videos, we're going to be presenting timeless astronomy education materials designed to help students learn science through inquiry, a way that research shows helps them better understand and better retain everything that they learn. In this first episode, we're going to introduce you to a special dose of comet-related material, and then in a couple of weeks, on January 28th at 6 p.m. London, which is 10 a.m. Los Angeles time, we're going to hold a second event to go over in-depth a variety of different activities and demonstrations that you can do in your classroom. You can register your intent to attend this next event on January 28th on our Google Plus page, and you can get to that page either via our YouTube page or via links that can be found on both cosmoquest.org's Educator Zone and on the GalileoTeachers.org website underneath resources. So this Hangout is being recorded live on January 14th, 2015, and if you're one of the awesome people out there watching this event live, you can actually participate with me and our guests using the Q&A app. You can access this app via the YouTube window that you're watching this in. There should be a little Q&A icon. Click on that at any time, type in your question, and I'm going to be following those throughout the show, and if you have any particularly awesome questions, I will pass those on to our guests. Right now, I don't see anything over in the Q&A app, but feel free to pipe up at any time. Our general plan for these activities is to bring scientists who are working actively in the fields that we're discussing onto the show to talk about how we're still learning new things about our universe. Astronomy and planetary science are not solved problems. There are new things waiting to be discovered every day, and there are thousands of scientists all around the world working at the edge of what we understand to push that wall out and bring new knowledge that will unfortunately make your textbooks, well, out of date. So we're going to bring them on to talk about what's new, and then we're going to talk to you and present demonstrations on how to help your students understand these new ideas in the context of inquiry-based activities that they can do in class. Today's episode, which, as I said before, is part of a two-part episode with the next part appearing on January 28th, is going to be about comets. Our solar system is littered with ice. The bulk of this material orbits quietly in our outer solar system, but sometimes something disturbs the ice and it comes plunging in towards our sun. In this Hangout, we will discuss the comets, how we explore them, and how they may or may not have brought water to worlds like our own planet Earth. One of the spacecraft that has been deeply involved in getting us our newest understanding of these comets, these icy bodies, is the Rosetta mission, which is run by the European Space Agency and launched in 2004. 10 years after launch, it pulled up beside the comet 67P Churyumov-Gerasimenko, otherwise known as 67P CG. And here to talk to you about these comets, we have a pair of European Space Agency scientists. With us are Nicholas Altobelli and Michelle Kuipers, and I'm sure I mispronounced those names, and as always I apologize for all names and welcome you to mispronounce my name at will as well. So welcome, gentlemen. Thank you so much for coming on our show.
Hello, good afternoon.
So you guys have been working on this mission, and when you got involved, I'm sure that there were certain scientific questions that you were hoping to answer, that other team mission scientists that you were working with were hoping to answer. What were these original questions that Rosetta was designed to seek the answers for?
Rosetta is the first mission that really looks in depth into a comet, the first mission that rendezvous with a comet and lands on a comet. And the basic questions to answer go really back to the formation of the solar system, the Earth. So the comets, as you already described, spend most of the time far from the Sun and are therefore more or less in the same state they were when the solar system formed. And they are kind of the leftover of the blocks that formed the planets in the early stages, and so give us some information about the material that formed the Earth and the planets. And this goes also into more specific questions, like if maybe the water in the Earth's oceans, or part of the water in the Earth's oceans, was brought by comets, and part of the organic material that at the end formed the life on Earth.
Yeah, and I would actually add, to put things in an even broader context, now there is lots of research on exoplanet. We have discovered other solar systems. We have up to 2,000 now and counting exoplanets. And actually, so it looks like planet formation is something very common in the galaxy. And we don't know exactly how you come from this dust particle mixed with gas originally to then end up with big rock body or rock gaseous body, etc. And I think comets, and we often present them as Michael said, as time capsule of this time, where you had an intermediate state of formation, not anymore dust, but not yet comet, and frozen in this state, witness of the physical condition of their formation location. These comets really bring all the information that you could not have now just close to Earth. This is material, as you said in your introduction, that you will have to, it comes to you for free, let's say, because they are brought into the inner solar system.
And the basic problem is that in the early solar system, while the planets were settling into their current positions, the sun was much, much hotter than it is today, and during this early period, it baked the inner part of the solar system dry. In fact, there's pretty much a line that passes through the asteroid belt that is the water line, with the comet Vesta on one side of the line, not comet, the asteroid Vesta on one side of that line, and the asteroid Ceres on the other side of that line, which is where we've seen Vesta appears to be dry, and we believe, based on early measurements, that Ceres is wet, and the Dawn mission will get there next summer and explore this difference. So Earth, on the dry side of that line, wouldn't have originally had water, and that water had to come from somewhere, and comets very much formed on the not just wet, but wet and frozen side of that early solar system divide. Now, the things that you've talked about with these basic questions, do comets have organics? Does their water match the water that we see on Earth? These aren't questions that we're going to answer with all of these stunningly beautiful images coming off of the spacecraft. What other instrumentation does the spacecraft have that allows you to get at answers to all of these questions?
Especially for those questions having to do with composition, there are several mass spectrometers on the spacecraft, so on Rosetta, that really collect the gas that comes out of the nucleus and measure the composition of the gas and also the composition of the dust. And there are also two mass spectrometers on the lander to try to really sample the material that is on or even within the nucleus.
Yeah, so there's really a great combination of two big types of instrument. The in situ one, as Michael said, where you really can sense the gas, you can catch the dust, and at the same time you can also perform remote sensing observation in all wavelengths, from microwave up to UV. And this is actually unique, that you're able then, with these two types of instrument, two main type of instrument, to disentangle some of the physical properties that you could not necessarily isolate with only one type of instrument.
And that's one of the things that I think people really need to understand about science is, well, in the news, most of the time what we see are these stunningly beautiful images. the reality is that science requires us to take data that isn't as beautiful as pictures we see, but contains completely different information and allows us, sort of like criminal forensic investigators, to figure out what is involved in, well, making a comet, essentially. So we have these big questions on composition, on organics, on basically what is the comet made of. As Rosetta has been able to fly up alongside this comet, and it's a misnomer to say that Rosetta is orbiting the comet. The comet really doesn't have enough gravity to allow an orbit. They're co-orbiting the sun, with Rosetta maneuvering around the comet. As Rosetta has flown alongside 67 PCG, what scientific surprises have come up? And I'm going to go ahead and pull up an image of the comet while you talk.
With the surprise, actually, I start with the topic of the composition of the water, so of the fusion that the water that contains heavy hydrogen, which turns out in this comet to be much larger than in the Earth's oceans, which means that at least comets with the same origin as 67P are most likely not the source of the water on Earth's oceans, and overall it seems to shift the evidence again a little bit more to be maybe asteroids, the sources, which comes as some kind of surprise, because a couple of years ago, the first time the D to H ratio in water was measured in a short period comet like Churyumov-Gerasimenko, it was exactly the same as in the Earth's ocean. So this is a little bit a shift of those ideas, and probably the main result there is that those comets that are on similar orbits now come from different reservoirs.
And for those of you who don't know, heavy water is water that, instead of being made of just regular hydrogen that has an electron and a proton, is instead made of deuterium, which is a heavier form of hydrogen that has a neutron in its center. And when we look at our ocean, we find that it's very rare to find this deuterium-based water, this heavy water with the neutrons in it. It's roughly 1 in 10,000 water molecules is this heavy water. When we looked at Comet, I believe it was Hartley 2 several years ago, it was found that the ratio between the regular water and the heavy water with that extra neutron in it, not neutrino, neutron, sorry for the misspeak, matched. Now, when we have then repeated this experiment with Rosetta, which is still fairly distant from the sun, the comet still isn't extraordinarily active, when that experiment was replicated, it was found that the amount of heavy water was so great that even one comet like 67 PCG, being part of making up the Earth's oceans, would have added so much heavy water that we would have seen a very different ratio here on Earth. Now, there's other factors that make heavy water different. It actually melts and freezes at a slightly different temperature. It freezes at a warmer temperature than regular water. So there's lots of neat physics involved. And can we assume that this experiment is going to happen over and over to see if different samples have different ratios?
It's true that one of the big plus points of Rosetta is to be able to perform this measurement in an extended manner, because we will, of course, follow the comet around this travel around the solar system, the sun. So, of course, this experiment will be repeated. But before going into possible different results of this experiment, we should also mention that this higher deuterium to H ratio is actually in line also with some prediction with thermodynamical models of the protosolar nebula, where actually the water gets vaporized and redistributed, and there is a separation of the deuterium-rich water and the less deuterium-rich water. And interestingly, if you look at some of the values that have been found in the last years, Enceladus, this is this icy moon around Saturn, which has also a kind of cometary-like activity, has value of D2H comparable to these hot-cloud comets, which are believed to have formed in the Jupiter region up to Saturn and have been then sent out to the outer, very far from the Sun by this possible migration of giant planets, the formation of the solar system. And at the same time, these measurements are actually in line with the prediction of thermodynamical model of the protosolar nebula, saying that the deuterium to H ratio should be much higher if the body formed where the protosolar nebula was much colder. So in a sense, the result is also, as you said, we are doing science, we make hypotheses, and we try to verify hypotheses with experiments.
And
actually, before the measurement at Hartley 2, what was now seen at Churyumov is about what would have been expected, yes.
And just to unpack a little bit of what you said, people often imagine that our solar system, the way it looks today, is kind of how it's always looked, and that's completely false as near as we can tell. It turns out that in the past, our giant planets were much closer into our sun, and there was a point in time where for every 2 times that Jupiter went around the sun, Saturn went around once, so twice for Jupiter, once for Saturn. And when you had both of these giant worlds lined up together, they were able to gravitationally perturb things and send them flying all over the solar system. So it wasn't that one day some great force came along and said, ice, go forth to the Oort cloud, but rather it was this moment in time where the interactions between all of the large worlds gravitationally started scattering rocky bodies inward, icy bodies inward, but they melt, so we don't see them anymore, and also icy bodies outward, as well as Uranus and Neptune outward. So our solar system was something that was greatly in flux in the past. Now, with the deuterium to hydrogen ratio matching theory not matching our ocean, this means that our oceans had to come from somewhere. Every little kid has so far been taught that the oceans came from comets. What are we going to have to teach them tomorrow?
They may come mainly from asteroids, exactly from this outer part of the asteroid, of today's asteroid belt, which will probably contain some ice, or which contains some ice. And also, as you described, with the migration of the planets, and with the planets also of the smaller bodies in the earlier phase, not all the objects have formed where they are now. So the asteroids are possible form, and comets are also still an option there.
Yeah, and also we should not forget that even very dry asteroids on the surface can, in the mineral, in silicates or hydrated silicates, you can contain a lot of water, which then gets released when you mentioned this migration of giant planets. It generated what is called the late heavy bombardment about 3.8 billion years from now. And the Earth was bombarded by asteroids, probably comet body as well, but then maybe the ice volatilized. And but as a result, with the high pressure and temperature in Earth, it was enough to release the water which was in the mineral lattice of this dry asteroid. So they are actually also called wet asteroid because of the large amount of water they're able to deliver on a less obvious way than volatile on top of a body. That's also a theory which is pretty much considered as of now.
And this is all why we have to keep finding new ways to explore, new ways to look at bodies, and why we can't just go to one comet. We have to go to multiple comets. We have to go to multiple asteroids. And science is really a partnership of different teams advancing our knowledge together. You gentlemen are part of exploring with Rosetta this one comet, and you work on other worlds as well. Other teams are out there as well looking at Ceres and Vesta. it's all part of a puzzle, and this isn't the only question that's been raised by this one particular comet. What other questions have been raised that you're now trying to answer in the data that's come back from Rosetta?
I would say one of the main point of Rosetta is really the therapeutic chemistry. I mean, what Michel mentioned this in the introduction, complex organic molecules, because we know now from you mentioned this synergies between different missions, different groups, and you know all these radio telescopes now, like ALMA, for example, they are able to trace organic molecules around stars and in the interstellar medium, and we start finding, and actually since a few decades, we find complex organic molecules. Now, how did organic molecules made their way to Earth? Because you needed them in order to trigger what we call now life. So life as we know it, based on carbon and water as solvents. So far we have, of course, spoken about the solvent, the water, but of course we need also this, what we call prebiotic molecules, the most simple molecules containing carbon, hydrogen, sulfur, oxygen, maybe phosphor. And with all of this, you made the living world as we know it. So what was the way for these molecules to find their way to Earth, where actually the physical conditions were probably not friendly at all for such molecules? They are fragile. So one thing that we are expecting from the comet is to make an inventory of its organic compounds and see if there is a way that this is probably the path that these molecules took to come to Earth.
And for those of you who don't know, organic molecules are molecules that don't have to be formed by biologicals. So saying that it has organics doesn't mean that there's anything resembling life. What it means, though, it's carbon atoms. So organic molecules are made of carbon atoms, and carbon is formed in most stars. Our own sun, excuse me, our own sun will happily produce carbon. And so when people say that humans are stardust, what they actually mean is we're made up of atoms that were formed in a variety of different stars. Some of them required supernovas. These atoms got redistributed into clouds of gas that within these clouds formed complex molecules that radio telescopes like ALMA are able to see. And then these clouds collapsed to form solar systems like our own, allowing missions like Rosetta to see the frozen bits that got left behind. It's all part of a large story, and you men are working out the details of this story. Are there any other big questions that have come up that you're particularly happy to be working with?
One other topic which of interest for comets and of cometary science especially is how does the cometary activity work? How does it work that when the comet approaches the sun, the surface ice sublimates, takes dust with it in some form, forms a coma, and from this later on through the interaction with the sun from the prominent tails that we can see in some large comets, the dust tail, which is the more yellow, and the bluish dust tail. And while the basic picture seems quite straightforward, it was actually never possible to maintain activity in an artificial comet in a laboratory, and also theoretically, it's really a difficult question. And there also, from Rosetta following the comet through perihelion, we hope to find clues how this really works.
There is one thing I found absolutely fascinating when we approach the comet, and it illustrates again the science based on hypothesis experiments. We thought from the ground-based observation that the comet shape would have a certain form which was inferred from light curve, basically by analyzing the reflection of the sunlight on the comet body. And when we approached in July, August, we started to see that the shape was completely different from what we had thought. And if you look at this picture now that you can see on your screen, you see how complex the geomorphology of the body is. You have pits, you have things that I don't want to call rocks, but they look like rocks. You have extremely smooth terrain. You have everything on this body, and you have to imagine, overall, it's not a piece of rock. It's something which is less dense than water. It's about 0.04 gram per cubic centimeter. It's amazingly full of void. And on top of that, the mass is so low, because the density is so low, that the gravity is extremely low. And despite of this, you see all these cliffs, hundreds of meter high cliffs. You see all this relief that we are just starting to understand. We don't know if, for example, it's a contact binary, if it's two bodies glued together at some point, or if a single body which has been, you see in the neck region in the middle, if it's a body which has lost lots of its mass because of some activity process that Michael was just mentioning. So one thing which is absolutely unique with Rosetta is the ability then to sound the interior of the comet. To get what we call a tomography of the interior, we will be able, or we have been able already, but the results are being analyzed, to transmit a radio wave inside the body and analyze the successive reflection. Every time a wave encounters a change in density, there is one wave propagated, one wave reflected. And from the analysis of these different waves, using also the lander, you're able to reconstruct how the interior looks like. And that brings us back to 4.5 billion years ago when these little dust grains started to aggregate. Did they aggregate to bigger body that then glued together, or did they just collapse due to some gravitational instability? We just don't know. And that's one of the coolest things that Rosetta will do, actually.
And it really is an amazing thing to be able to see a comet up close while it's inactive, before all the jets have formed, before it has a big coma, before it has a big tail. And the mission's going to tag along as close as it can while maintaining safety as it gets more and more active, and we'll get to see the surface change. I know personally the thing I've found most amazing is there's boulders on the surface of this, and there's so little gravity. The Philae lander, the amount of gravity it felt was what a normal piece of paper experiences here on the planet Earth. So to think about a spacecraft feeling like it weighs as much as a piece of paper is pretty amazing to think about. Now, you've brought up a lot of the answers to this question, but I'm going to ask you guys to somewhat summarize. If you wanted to encourage other people to look to comets and try and understand them, what would you tell them is most important about studying comets and why we need to keep doing this?
The first thing that would come to my mind is try to make the difference between what is pristine, what is the original state you want to study, and what is linked to the history of the body of the solar system. I think that's fundamental to be able to say, oh no, this is due to space weathering, this is due to activity pattern, this is due to the sun baking the surface, and this is due to the origin of the solar system.
Anything to add?
No, not much to add to that.
So, Rosetta, can you tell us a little bit about what it has left as CP 67P CG sneaks up on the sun?
Yeah, I mean, what is still coming in the future is the time where the comet is really active. I mean, we see the activity now. We see the jets have nice pictures and also measure the data in situ. But at the perihelion, at the closest point to the sun, the comet will be around 100 times more active than now. So about 100 times more material per second or per time will leave the comet than now, and then we can really see the development, how the activity develops with time, and also, essentially the investigate how the changes associated with it also on the surface of the comet. We can also see how the surface evolves with the activity and how kind of the activity and the surface and also the inner part of the coma work together.
It will be a great time, and you have to imagine because the comet is inclined, the rotation axis is inclined, there are regions on the comet which have not been illuminated for the last 6 years, let's say, and suddenly they will be exposed very close to the sun. So probably there will be a firework there of activity.
It's going to be awesome to get to watch. Now we have one question coming in from the audience before I let you go. Hugo Berman is asking, can we assume that the organic molecules were already in situ in comets, or have they been formed due to reactions on the comet?
This is an interesting question. I think the temperature, probably the kinetic of formation, this type of molecules probably form best in also cold molecular clouds where dust can help as catalysator. I am not sure, and I don't think that the conditions were right for formation in situ in the comet. I think it's material which has been brought from the interstellar medium in the protosolar nebula and kept intact because the comet formed so far from the sun. That would be my primary reaction.
Yeah, my reaction is the same. Most of those molecules probably formed already in the grains that formed the comet out of a molecular cloud or the protosolar disk. Now, if you have further chemical reactions within the comet itself, it could be, but I would guess that the bulk happened before. And by the way, something else that motivates this are some existing results. So amino acids, for example, have been found in meteorites, and actually an amino acid was also found in the material that the Stardust probe collected from the coma of Comet Wild 1. So there are already some existing results that also motivate the more detailed study of what we can find in the comet in terms of organic material.
And you have amino acid in the interstellar medium as well. So like glycine, it's kind of everywhere. So you just need a way to bring it to Earth.
And this is where at least we're going to be grabbing samples from Bennu with the OSIRIS-REx mission that's coming up. And there's always new missions looking to capture data in new ways. And we've had past, as you mentioned, the Stardust mission, which got parts from Wild 1 rather. So it's a long-term process with generations of scientists and instruments involved in advancing our understanding. Any parting thoughts that you want to leave our audience with?
I would say one thing is humankind tried to explore its environment. You mentioned exploring one comet, what does it bring us? In general, centuries ago, we discovered new continents. Now we are discovering our solar system, which is our immediate environment, and we are also with telescopes trying to study our environment a bit further away. But the primary goal is discover, explore the environment. Don't stay at home. Try to see what is around.
That's excellent. So thank you so much for joining us from outside of Madrid and being part of helping people understand how to explore our solar system and understand the universe that we all share. So thank you so much, gentlemen, and
thank you. Cheers.
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 Bye-bye.
So this hangout, as we introduced earlier, was put together as part of the Inspiring Science Education series to help people understand all the resources that are out there that allow us to bring science into our classroom more effectively using the inquiry method. We are working in this project thanks to a variety of different people, and with me today is the director of the Galileo Teacher Training Program from Nucleo, Rosa Duran, and she can give you an overview of this project, and I'm going to work on bringing up the websites that will help you better understand where to find all the materials that we are creating and that you can use in your classroom. Rosa. You're muted, Rosa. I unmuted you and you muted you. Okay, I'm not touching anything. Please unmute. Sorry, audience.
Okay, can you hear me?
Yes, go ahead.
Okay, so hello everyone. Welcome to this that is already starting as a brilliant series of events. As Pamela said, we are trying to bring to classrooms, in particular in Europe, through the Inspiring Science Education Project, cutting-edge tools and resources for science education, and nothing better than starting with something that is very hot in science research as the Rosetta mission. or should I say cold, very cold, getting to be hot in the near future. So as Pamela was saying, this is the first of a series of sessions where we will be sharing with you cutting edge science, and along with that we will be adding lots of tools and resources, cutting edge tools and resources for science education, and walking with you on the use of these resources in your classrooms. So nothing is more annoying than finding that when you come to talk about teaching science, we tend to go back to a zone of comfort where everything is understood, all the tools are already very used and tested, and we are not scared of walking the road towards that particular topic. Here we are exploring new places. We want to have your outdated textbooks put aside and have you diving into the world of new science in classroom. This series of Hangouts are particularly devoted to teachers that are members of the Inspiring Science Education family. If you are not a member of this project, please join hands with us. It's a project where we are willing to share what's new and modern, not only in science, but transforming this science into something that teachers can easily share with their students in classrooms. So our work here is to produce a series of scenarios, that's what we call them, where you will find examples on how to teach, for instance, what you learn with the scientists today, with the students now, not having to wait this to appear in textbooks. So this is the main purpose of Inspiring Science Education. Not only that, so it's a very rich project where you will find first a series of thematic communities where you can freely share tools and resources with your colleagues and with other colleagues from all over Europe and other countries. A place where you will find thousands of resources that can be tailored to your needs, but also a space where we will be sharing with you scenarios that are built using the inquiry methodology, or in other words, the scientific method in classroom. They are built and thought for you, started for you. We have a series of examples that we call demonstrators, and we will be sharing them with you, showing them to you, sharing with you the ideas that we have behind them, and inviting you to test them in your classroom, share the results with us, help us enhance these demonstrators, and spread it around the world so that people can have modern science in classroom now. So I will be asking Pamela, do you think you can share the link to our demonstrator and perhaps put the demonstrator on the screen so we can share with the teachers what we've been preparing?
So sharing links is more difficult. We have everything linked off of the Galileo Teacher Training Program website. If you go to galileoteachers.org, click on Resources, and drop down to Inspiring Science Education, everything that you need is here. We're also going to be linking everything off of CosmoQuest's Educator Zone.
Well, actually, it would be nice if everyone could become members of Discover the Cosmos community.
And that's what this is instructions on how to do. So if you go to the Galileo Teacher Training Program website, what it does is it tells you to, first of all, join GTTP. It gets you lots of interesting newsletters, alerts you on activities available all around the world, and will allow you to earn badges for your participation in this program. Now, the other thing that's the most important thing to do is to click this Discover the Cosmos Community in the ISE website link. When you click that, it takes you over to the Discovering the Universe. I'm already logged in, so I'm getting an error. It works if you're not logged in. So click that link while you're not logged in, and it will show you how to log into the site and become part of this community. Once you're part of the Discovering the Cosmos community, you'll be able to see all of the members, all of the activities, all of the resources. Now, along with each activity, we're going to create a new sub-community. The sub-community that is associated with today's activity is the Chasing Comets sub-community. When you join this sub-community, you'll be able to see all the different resources that we're creating, and I apologize, this page, I didn't preload it, so while that's loading, I'll stay on this page. You'll be able to see all the different resources that we have picked as being our favorites. Along with all of these resources that we're giving you to use, we're putting together a dedicated activity that shows you at least one route to bringing all of these different activities into your classroom. So you can either search the existing educational resources, this is the page that we were waiting for it to load, or I'll give you a sneak peek of the resource that we're going to be presenting on January 28th. So this will be public for you on January 28th. This activity is called Digging into Comets. And as part of this activity, let me skip through all of this stuff to the next section. As part of this activity, we have, following the 5E methodology for teaching with exploration and elaboration and evaluation, we've put together an activity that starts out with the kids engaging with you, the teacher, in building a comet and learning about the different aspects of a comet. From engaging in a comet, you then move through to developing a hypothesis on, well, where might comets come from? Why is it that they melt when they're close to the sun, but they exist for thousands or even billions of years? Students will go on to figure out how to solve these questions using Celestia, and then dig in to actually do their analysis in Celestia, where they'll be looking at comets. They also have the chance to use Celsa-J or Astrometrica to explore the motion of comets, and of course, like every good project, we have ways for them to elaborate, to try and take the data that they've looked at and use it to try and understand the origins of where comets come from, and we give them a chance to evaluate the things that they've learned, to think for themselves, what do I know now that I didn't know yesterday about how our solar system is put together and the origins of the material that is within our solar system.
I also would like to add that this particular project has another feature that might prove important to you, which is means to assess the development of problem-solving skills of your students. So the demonstrators are coming with PISA-like assessment questions that you can use with your students to evaluate how they are developing their skills while engaging in the project. Also, you will have the capability to clone the example that Pamela just showed, and adapt it to your own needs. Use the parts that you like from the demonstrator that we've created, and just reshape it the way you want, or to create your own scenario. We are going to be producing tutorials on how to create your own scenario, how to clone and use the one that we've created, how to use the different tools that we are using in the framework of the scenario, like, for instance, Celestia and Astrometrica, as Pamela told you. Pamela, do you think you can click on the preview that the teachers will see of that example that you are sharing with the audience, so that they can have a look of the environment that the other teachers will find, and also the same environment that the students will find when they are in the lesson?
It's working on loading. I'm afraid it's a bit slow at the moment.
Also, you can, in the scenarios, you can add formative questions, you can add videos, you can add images, as Pamela already did in the demonstrator that she was showing to you.
So this is a fancy way of saying, very simply, you can take everything we've done and you can edit it. You can adapt it for your own classroom, and we fully recognize that the challenges that you face in your classroom are specific to you, to your region, to your set of students. But other people can benefit from the adaptations that you make. So when you take this lesson and you download it and you edit it, share what you've done by uploading your changes so that other people can benefit from the things you do. We're trying to make it easier for teachers around the world to get science into the classroom. We're providing educators' guides, instructors' guides to go with each lesson, bigger versions of the graphics that you can easily show up on the projectors. We have assessment questions that are involved in everything. You can work with all of this to understand what your students are learning and to innovate on how science is done in the classroom. So please join us in making sure that science is easier to do for students everywhere in the world.
Pamela, I would like to add as well that all the information and materials and resources, including information about the Hangouts, the dates, and everything that will come out in the next 2 years, as you said, it's quite fun ahead, will be available in the Inspiring Science Education website and portal. So they can also find all the information there, and will be announced through the social media of the Inspiring Science Education project as well.
So we'd encourage all of you to follow Inspiring Science Education on Google+, to subscribe to our page on YouTube, and to plan to show up on Wednesdays at 10 a.m. Pacific, 1 p.m. Eastern, 6 p.m. London, 9 p.m. Warsaw, and join us in working to get education out there. This is a sister hangout to the Learning Space Hangout that is being produced by CosmoQuest, and we're going to work to make Wednesdays the day that educators get all the tools they need to, well, bring science into their classrooms. Now, CosmoQuest is a place that produces resources. Galileo Teacher Training Program is the place that trains the teachers, and Inspiring Science Education is the hub that holds all of the resources that you need. Science education, like science research, is a partnership of many different people contributing many different things. Can you tell our audience a little bit about the Galileo Teacher Training Program?
Sure. The Galileo Teacher Training Program was a program that started with the International Year of Astronomy with the aim to train teachers all over the world on the use of tools for astronomy education, with a special emphasis on digital tools for science education. We've been partnering with several important projects across the world, and this year we are partnering with the International Year of Light, of course, and all of this is being created, and we are hoping to leave a legacy behind in everything that we are being involved in. And I think I can mention that everything that is happening here will be assembled into something that we are calling the European Science Education Academy, where the Galileo Teacher Training Program is collaborating with. And the good thing about the Galileo Teacher Training Program is that we're global. We are represented in over 100 countries. We have, I think we're quickly approaching 50,000 teachers trained all over the world. And this is very strong and sustainable. It's a group of volunteers all over the world that leaves a remaining legacy. And we are building on efforts like Inspiring Science Education to leave an even bigger legacy behind. So you're here to stay.
And this is currently, with 2015, the International Year of Light. And this Hangout series is going to be cross-produced, cross-promoted with the International Year of Light and go out via the 365 Days of Astronomy program as well. So we're working to create something awesome and global, and through the ISE European framework, we're going to be aligning everything with the big questions in science, and here in the United States we'll also be aligning everything with the next generation science standards. And if we have volunteers anywhere else in the world who would like to help us figure out how to align what we create with other standards to help things reach out to other communities, we'd love to hear from you. And you can reach us at ise-hangouts@galileoteachers.org. And we're here to help you however we can. So I mentioned that on January 28th, we're going to come back together to go over in detail how to use the ISE interface to download and clone the materials, introduce the materials that we've created so that you know how to use them in your classrooms. Is there anything else that our audience should look forward to on January 28th?
I think that you assembled everything. By then, you know, the portal is something that is under production now. Many features are happening every day. New things are coming up. So on the 28th, we will share the news, and we will keep doing so along the year. Every time we have a Hangout, I'm sure we will have something new to share with the teachers. And also, one thing that I forgot is that we are assembling all this into online academies, but we also have face-to-face academies where teachers can participate via the Erasmus Plus funding. Those that are in Europe know which funding that is. So if you're interested in participating in summer academies, spring academies, winter academies, keep in touch with us. We will provide more information about how to participate on those.
And every summer we do have a teacher training program that I believe is located in Greece.
Yeah.
And we hope to see you in Greece. Last summer it was quite amazing. It was in the city of Volos. And there's nothing quite like being on the sea discussing a science that really got its modern origins in nations surrounding the Mediterranean. So this has been our first hour, and we're glad that all of you have joined us. I see out there Georgia Bracey, Hugo Burnham, Nancy Graziano, Michael Joven. Oh dear, I'm so sorry what I'm going to do to your name. Dejan Crucial. Sorry. You may mispronounce my name at will, Cecil Morgan, and so many more of you. Thank you for joining us for the past hour. Please subscribe to our YouTube channel, follow us on Google+, and register to become part of all the awesome things we are doing. And if you want to go out and participate in science right now, go to cosmoquest.org, where you can work on mapping out the rocky parts of our solar system. Thank you so much for joining us.